Welcome to the course on plasma physics and application to fusion energy, astrophysics and industry. My name is Duccio Testa, and in this lecture we will be discussing performance and operational limits of tokamaks. Okay, so first we will be looking at critical parameters for a fusion reactor. This will lead us to describing operational limits, and we will see that there are two kinds of operational limits, soft and hard limits. This will lead us to describe three different kinds of operational limits on the plasma current, on the density, and on the pressure. And finally, we will end up with describing disruption, which is the ultimate consequence of violating these operational limits. Now let's look at the fusion performance. Let's briefly review what we did in lecture 6. What we found is that for thermonuclear fusion to be economically attractive, we need an engineering fusion energy gain, QE, that is in the range between 2 and 10. And this corresponds to a physics fusion energy gain, capital Q, that has to be in the range 10 to 40. We also know that to achieve this sufficiently high capital Q, we need to have a sufficiently high value of the triple product N, T, tau E. So we ask ourselves our question: what are the factors limiting the fusion energy gain capital Q? Now, the first thing that we know is that the energy confinement time is observed to increase with the plasma current, IP. The fusion reactivity is proportional to the square of the plasma density, N square. And then if we work in the typical temperature range that is optimal for fusion reactor, which is in the range between 5 and 15 keV, in this temperature range, the fusion power, P, increases as the square of N times T. So NT square, fusion power is proportional to the square of the plasma pressure. Now we have seen immediately that there are three main factors for fusion performance: plasma current, IP, that leads to the energy confinement time, then density and pressure, P. And in fact, these three quantities, IP and MP, are limited by different mechanisms. And these are the operational limits in tokamaks. If we approach these operational limits, then we end up in disruptions when we go over this limit, and this is a hard limit for the operation of a plasma, or we end up with confinement and degradation, and this will be a soft limit. Now, the way to describe these operational limits in tokamak is the UG diagram that provides a link between the plasma current and the density for which safe operation is allowed in tokamak. The UG diagram describes the quantity 1 over QA, QA the safety factor at the plasma edge, that we have seen is a measure of the total plasma current, as function of what we call the Murakami parameter, that is proportional to the plasma density N. So what we have here is the definition of the axis for the UG diagram. On the x-axis, the Murakami parameter, N, as written here with the bracket, is the volume average plasma density, which is multiplied by R0, the position of the magnetic axis, divided by B phi 0, the value of the toroidal field on axis. This is the Murakami parameter. On the y-axis, we have 1 over QA, that is proportional to the total plasma current. So the first limit, it's a hard limit on plasma, is given by total plasma current. And this limit is set by global MHD instability that impose a 1 over QA lower than 0.5 hard limit. And this is really a hard limit. It's independent of the plasma density. Then we have a density limit, is a soft limit. It's called the Greenwald density limit. This tells us that if we want to operate a larger density, then we need to increase the plasma current, and correspondingly by increasing the plasma current we can work a larger density. This is basically a line that is oblique in the y-x diagram. What we have here is our definition of the operational space of a tokamak in this range here. This is the safe, this area here is the safe operational space for a tokamak. On the top we have in fact a limit on the total plasma current, and this diagonal line is a limit on the density. What is important to note is that if we shape the plasma, then we can exceed the Greenwald density limit. In this sense, it's really a soft limit. Now, another operational limit is due to the plasma pressure. And in fact, the ideal beta limit is set by the occurrence of ideal MHD instabilities. These are instabilities that work on a very fast time scale, and in fact, there is not possible to control these instabilities in real time. Now, if we collect data from many experiments, as it is shown in this graph here, for many different machines, we find that there is in fact a scaling between the maximum volume of beta in percent and the ratio between the plasma current IP, the minor radius A, and the toroidal magnetic field on axis B phi naught. If you look at this graph, where we have the toroidal beta plotted as function of IP over A B phi naught, we need the different machines are basically all aligned under this dotted line that corresponds to a value beta n 3.5. 3.5 is the definition of the normalized beta, beta divided by this normalization factor, IP over A B phi naught. This range of normalization, C beta, beta n, in fact can be between 2 and 5, and increases when we optimize the plasma shape. So if you look again at this graph, we see that in fact the first machine like Tosca and TFTR, these were circular machines. The plasma cross-section was a circle. And in fact, all these machines set up really at the limit of beta n equal 3.5, if not even below. However, we noted that there is one particular machine in this graph, is the D3D machine, that in fact for certain value of IP of A B phi naught, clearly we obtain a toroidal beta that exceeds this 3.5 limit. In fact, if we draw a line taking this value, this line would correspond to beta n in excess of 4, perhaps even 5. So this tells us what we can do to increase the beta limits of the plasma pressure limit on tokamak, because this D3D machine is a machine that is shaped. The poloidal cross-section is elongated, and it has actually also a triangular, quasi-triangular shape. So this, in fact, by optimizing the plasma shape, then we can go beyond this traditional Trojan limit beta n equal 3.5. And in fact, this also defines the range of operation that we can expect in future plasma devices, such as ITER. Now, what we find, however, is that resistive MHD modes can degrade the confinement at beta below the Trojan limit. So we do not manage to get to this value beta n 3.5 due to these resistive MHD modes. However, these modes are resistive, so they work on much slower time scale than ideal modes, and then we can do real-time control of these instabilities. Now, if we really exceed hard operational limits, what we end up with is a disruption. Here, we have a plot that describes the evolution of a plasma current for a jet discharges that ends up in a disruption. It is characterized here by this sudden drop of the plasma current. If we lose the plasma current, and we see the time scale here is very short, millisecond, then the plasma confinement is lost because we lose completely the poloidal magnetic field. What is important to note is that accelerators are in principle disruption-free because there is no inductively driven toroidal plasma current. All magnetic field is provided by external coil. We can look here at a photo of a disruption in jet, and we see these patches of red along the plasma wall. We see one here at the bottom of the machine, and clearly in this area of the machine, in the I field side. In fact, these patches of red are in fact area where the plasma touches the wall. So in a disruption, we can have damage to plasma-facing component when the heat flux exceeds the limit of the material. So if we look at future fusion devices, such as ITER, but ITER, we can only have 5 disruptions that are allowed over its entire 30 years long lifetime. And in fact, the problem of disruption is major that we are studying. There are disruption mitigation techniques that are under development, and these mitigation techniques works on a real-time basis. And in fact, the principle we can see here, if we go back again this plot of the plasma current, we note that just before the plasma current drop, there is a slight spike in the plasma current. So I can just highlight this section. Plasma current is flat, there is a spike, and then it drops. This is a very short time scale of the order of a millisecond or so. But in fact, this spike in the plasma current is what we call a disruption precursor. If we can detect it, and we usually can detect it very efficiently, then it is possible to apply disruption mitigation techniques that in fact mitigate the damage to the plasma wall due to a disruption. We can now summarize what we have seen today. The plasma current IP, plasma density N, and plasma pressure P are of utmost importance for optimizing a fusion reactor. These parameters are constrained within limited operational range, which are described by theoretical and empirical scaling laws. If we approach these operational limits and when we exceed them, well, this may lead to disruption, which is a hard limit, or to confinement and degradation, which would be a soft limit.